Good afternoon, class. Today we're going to be looking at exponential functions, and you'll notice, or hopefully you'll notice, this looks different, doesn't it? Yeah, then when you click on the homework, it looks different, and there'll be more information on each page. Here are the problems where you click to see the videos, and then you gotta click them if you want credit for it in the homework either way. And so, what do y'all think? What do y'all think of this? The menu is different, and hold on. And I need to do some talking about, some of this is going to be a review if you took Math 371 at this school. And some of it will be new. This is a long assignment, I'll tell you that much right now.
Not a real difficult one.
And here we go. I'm going to start off by defining a zero exponent. Zero exponent. At this point, I'm going to be using the letter B for base of an exponent a lot. And we're going to assume, whenever you see my letter B, assume that B is a positive number and that B doesn't equal 1. I guess it could be 1 in this case. I'll just say...
well, still, 1 to any power is 1, so...
B to the 0 is defined to equal 1. So when we look at number 1 in the assignment... 46 to the 0 power. Any non-zero number to the 0 power is defined to equal 1. Do I need to write that problem down? No? Okay. And switch over here. Switch to the paper. I have one for you. Pi, that's the ratio of the circumference of a circle to its diameter, approximately 3.14. Pi to the 0 power. What does that equal? 3.14 to the 0 power is still 1. So the point is, doesn't matter whether it's, as long as it's not 0 to the 0. 0 to the 0 is undefined. That's just meaningless. Next.
Wait, I want to show them. In order to raise an exponent key is this little caret top here. 0 to the 0 power, error. Okay, you can't have it
a base of 0 for an exponential
What was that number
expression.
1? 46 to the 0 power? Anything to the 0 power is defined to be 1.
Now, negative exponents.
So now, the first problem is about a 0 exponent. Then we start looking at negative exponents.
Our concept of exponents as repeated multiplication sort of falls apart when you look at a negative exponent. Because if you have 3 squared, that means 3 times 3. You have 2 factors of 3. But if you had 3 to the negative 2, you can't count out negative 2 threes. Negative 2 is an accounting number. I'm going to state this property involving negative exponents in 2 cases. First of all, b to the negative n is the same thing. A base to a negative exponent is really just saying the reciprocal of the base to the positive exponent. And suppose this base weren't just were a fraction. Suppose we'd had something like a over b to the negative n. A negative exponent means the reciprocal. The reciprocal of b is 1 over b. The reciprocal of a over b, if you have a fraction to a negative power, flip the fraction and change the exponent so that it's positive. To illustrate, looking at number 2, let's see. Here we are, number 2. We're told to evaluate, let me write this down, 1/5 to the negative 2 power. That can't mean 1/5 times 1/5 times 1/5, negative 2 times, because as I said, negative 2 is an accounting number. If you have a fraction to a negative power, you flip the fraction. If you were to flip 1 over 5, what's the reciprocal of 1 over 5? 5 over 1. So I'm just going to say a 5 to the positive 2. 1 over 5, when you flip it, becomes 5 over 1. And 5 divided by 1 is just 5. So 5 squared reduces to 25. 1/5 to the negative 2 power reduces very nicely to 25. Any questions there? Okay. Oh, number 3. I like this one. Okay. 2/3 to the negative 3. 2/3 to the negative 3 power. Okay, I see that I have a fraction to a negative power. To get rid of, change that exponent from a negative 3 to a positive 3, what do I need to do? Flip the fraction so that 2 over 3, because of this minus sign here, the 2 over 3 is becoming a 3 over 2. So we have 3 halves times 3 halves times 3 halves. That's like 3 cubed. You could think of it as 3 cubed over 2 cubed.
Be careful, don't say 9.
What's 3 times 3 times 3? 27 all over.
Don't say 6.
2 times 2 times 2 is 8. For 27/8 as my final answer. Any questions there?
So 2/3 to the negative 3 is 27 over 8.
Well, not really multiplying. You're saying 3 cubed and 2 cubed. You're applying. And let me show you why you can do that. Let me show. Okay. That's saying 3 halves cubed. That's it. That means you have, because you've changed that negative 3 to a counting number. That means you have 3 halves. 3 halves times 3 halves times 3 halves. And to multiply fractions, you multiply the numerator. 3 times 3 is 9, times 3 is 27. 2 times 2 is 4, times 2 is 8. That's why you're able to do that. Okay? That you're right. So what did he say? What was the phrase?
She said, multiply by...
3 times 3 times 3 is 27. 2 times 2 times 2 is 8.
The fact that there wasn't a 1 on the bottom is why 5 over 1, we just wrote as 5.
Yeah, you're right. Technically, there was a 1, and 1 squared was 1. 25 divided by 1 became 25.
27 over 8. I have to get harder.
Okay, this is number...
where does it say the number? Just a question.
It must be 4. Okay. All they want to do is they want us to write it using a positive exponent. A to the negative 3. Okay. They want us to write that using a positive exponent. I think it's this first line here, this first statement I wrote using involving negative exponents. You have something that's not a fraction raised to a negative exponent. That becomes 1 over a to the negative 3 becomes a to the positive 3.
This negative here is that 1 over.
Any questions there?
You know, in algebra, you always do it one way, then do it in reverse.
So we type in
1 over a raised third power.
Next. Okay, now they want us to write this using a negative exponent. They've given us something that doesn't have a negative exponent, and they want us to write it with the negative exponent. So this is number 5. And I don't like the way you can't see the question number right up here at the top. I'll tell you that much right now. I don't like that.
It used to say question 5 up at the top.
Mm-hmm.
Yeah.
Okay, well, switch to my paper. Yeah. Okay, I need to rewrite this using a negative exponent. I think it's this statement here in reverse, the one we just used for number 4. How do I write 1 over 7 squared? It's just with a negative exponent. I drop the 1 over. To drop that 1 over, what's going to happen to the exponent? So it's going to become a 7 to the negative 2 for my final answer of 7 to the negative 2 power.
So we're not going to put a 49 anywhere. It's not asking about that. It wants us to write it as 7. Oh, where's the exponent? Oh, raised to the negative 2.
Any questions there? And I need to write some more. I guess we have one more of these. Let's do one more. What is that? This is number 6. We want to write using a negative exponent 1 over n to the 7th power. 1 over n to the 7th power. Okay. Okay. Drop the 1 over. You have an n. You change that exponent 7 to the negative 7. So n to the negative 7 power.
It's the same thing as 1 over.
This is a long assignment, but hopefully you see some of the problems are pretty fast. We're already down to number 6, and we've only been recording for 13 minutes. There are times we've been going an hour and we haven't done 6 problems. So here, we're going pretty fast. Now, it won't stay that easy, but
it doesn't.
Okay, I need to write some more.
Oh, yeah.
Okay.
So you've looked at a 0 exponent.
We've looked at 0. Okay, suppose the exponent is 0. Suppose the exponent is negative. Suppose the exponent is a fraction. Okay. I'll say fractional exponents. I recall when we were solving radical equations, we ran into exponents of 1/3, and we said that, let's see, I'm going to state several statements here. First of all, b to the 1/2 power, a 1/2 exponent is just another way of expressing a square root. So b to the 1/2 is the same thing as the square root of b. Whereas, I remember 1/3 exponents popping up with those radical equations. B to the 1/3. That's another way of expressing, if it's a the denominator is a 2, you're looking at a square root. If the denominator is a 3, you're looking at a cube root. And we can keep applying that logic, expanding it. If it's a b to the 1/4, what sort of a root would it be? A 1/4 power is the same thing as a 4th root of b. Let's generalize that. Let's generalize this. The nth root of b. Oh, no, I went the wrong way. b to the 1 over n. b to the 1 over n. If you see a fractional exponent, 1 over a number, that number there is the index on the radical, and the base is the radicand. A zero exponent, a non-zero quantity raised to the 0 is defined to be 1. A negative exponent is another way of expressing reciprocals. A fractional exponent is another way of expressing a radical. Let's look at numbers 7 and 8. Okay, rewrite without rational exponents and simplify if possible. This is number 7. And let me write the problem down. X to the 1/4 power. X to the 1/4 power. Well, that 4 right there says we're looking at a 4th root. And what are we going to have under the radical? X, for the 4th root of x.
Wow, it looks like you just wrote the problem down and wrote out the answer.
That's right, but
so there's no steps.
There's no steps, but you got to know what they mean by a fractional exponent.
So
Mm-hmm.
type that in. Click here.
Hey, wait a minute. Look, we're not using the square root key. Do y'all see the little hot button that has that blue box where the index goes? What are you going to type right there in the little flashing blue box? You type the 4, and then underneath the radical you type an x. Any questions there? What about number 8? Hopefully it's just as easy. Okay, number 8. We have 64 to the 1/3 power. (64 to the 1/3 power. That's a 1 there. It's hard to see that there. That 3 down there says we're looking at a cube root of 64. What's the cube root of 64? Here's what you're thinking to yourself. You're thinking to yourself, what number can I cube to give me 64? What number can I cube to give me 64? What times what times what? 4, let's see, I think that's right. 4 times 4 times 4. 4 times 4 is 16 times 4. 16 times 4, sure enough, it's 64. So the cube root of 64 reduces to 4. Any questions on my logic there? Here's my scratch work. I'm thinking to myself, what times what times what gives me 64?
Oh, the square root of 64 is 8.
But the cube root of 64 is 4.
Let me write that or punch that.
Okay. Now, I need to switch over to my paper. I need to write something else. These properties that I've listed here all assume that the numerator of that fractional exponent is a 1. Suppose the numerator is not a 1. Suppose instead of a 1 over 3 here, we'd had a 2 over 3. Okay. B to the A over n power. I should have colored these things. A is blue and n is red. Okay, you're right, Tony. Hold on. B to the A over n power. The denominator tells you what sort of a radical you have. That's saying the nth root of b.
So
the nth root, the bottom there,
is the root.
The top is the power to which you apply that expression.
So
And you say, well, what about that 1? The way this is saying, it says the cube root of 64 is 4, and then you raise it to the first power. 4 to the first stays a 4. Suppose instead they had asked us to find this. Suppose we had needed to evaluate 64 to the 2/3 power. That would have been a cube root of 64.
bottom number's the root.
The top is the power to which you apply all of this quantity. Now, I will mention right now, you could take the square and put it underneath that radical and have 64 squared, but if you put that exponent under the radical, then you're going to start getting huge numbers. So my advice to you, the denominator is the index on the radical. The numerator is the power that goes outside the radical. Because what's for the cube root of 64? We've already figured that out. The cube root of 64 was, so we had a 4. We got a 4. Now we have that 2, that 4 squared. The 3 says take the cube root of 64. The 2 says square the result. What would this answer be here?
4 squared.
16, I agree. So it's not bad, even if the exponent, even if the fractional exponent has a numerator other than 1. That's not too bad. Let's look at number 9.
Ooh.
Oh, okay. Let me write that down. That's 625 to the 3/4.
Top number is the power, the bottom number is the root.
That says we have the 4th root of 625. That denominator there means you have the 4th root of 625. And then we have to cube everything. What's the 4th root of 625? What times what times what times what equals 625? Here's my...
Move it.
Yeah. Okay. We want to know, here's what we're asking ourselves. What number to the 4th power equals 625? I know one thing, it's got to be bigger than 4. Well, I don't really know that, but 4 to the 4th is 256, so I know it, but...
You know.
I know it, but probably you don't notice that. So, let's see, let's go to our calculator and play around. What number to the 4th power will give us 625? When I look at that last digit there, 625, it's not 2 to the 4th. I think it's going to be 5 to the 4th. Check 5 to the 4th. Well, 4 to the 4th is 256. That's okay. So the 4th root of 625 is 5. So we have 5, but we're not through. What do we have to do with that 5? Cube it. 5 times 5 times 5.
Say 15.
They wouldn't. These students are smart, Tony. They're sharp. 5 times 5 is 25. Times another 5 is that 125? Okay, now, if you're using a calculator like this, I guess I'll go ahead and show, make sure y'all are aware that a calculator like this, you can take the 625 and raise it. What's the exponent? 3 divided by 4. What do you think that should give us? What did it better give us? 125? Sure enough.
But notice what he did. He put that exponent in parentheses. You have no idea how many students in business math, we do have a lot of stuff like this to do, and students do this. And then ask, oh, what's wrong? Look at that.
Without that 3/4 in parentheses, you have to perform the order of operations, which means you perform exponentiation first. That what he wrote there, he took the 625 and cubed it. And then he took that huge number and then he divided it by 4. He performed the exponentiation of cubing and then the division. In order to have an exponent, a fractional exponent, you have to enclose it in parentheses. Any questions?
That's the thing. You must enclose the fractional exponents in parentheses. Like number 8, if you do this, 64 raised to the 1/3, it's going to give you the wrong answer. We know the answer is 4. Look at what it gave us.
It took 64 to the first power is 64 divided by 3 to get 21 and a third.
Sometimes students say the calculator messed up. No.
No, the calculator didn't mess up.
You messed up punching the stuff into the calculator.
You're so negative, Tony. That's why they like me better.
Well,
they told me as much.
They didn't really say it.
I could just sense it. I could sense it. Okay,
wait, I got to punch in the answer of this one.
125. I just keep wanting to reach over there and grab that mouse and do it myself after, doing it by myself those days. Now I'm just going to keep on grabbing that mouse and punching in those answers. You should have seen me. You would have been so impressed, Tony.
25 to the 3/2 power.
25 to the 3/2 power.
It's not a hard problem, but if you don't know what that 3/2 is or how to work with it, it's darn near impossible.
I'm going to do this the way we've been doing it. I'm not going to use a calculator. If you want to punch it in with the calculator, fine. But what I'm going to do, I'm going to write it out the way I was doing the other stuff. Because you're going to have to know how to convert these fractional exponents to radicals and vice versa as we're working with logarithms. These properties of exponents are not going to go away over the next 3 assignments. That denominator is a 2, so what sort of a radical are we going to have? Just an ordinary square root, okay. And you put the 25 down here. What am I going to do with this 3? It becomes the exponent. What's the square root of 25? Oh, okay, 5. And then we're cubing it. It's just a coincidence. 9 and 10 both give us the same answer of 125. And why did I box in this answer? I like to box in or circle my answers and close them in some sort of figure because that's pop psychology. You do that, that says, okay, I'm through with the problem. I'm ready to move on to the next one. I remember learning that in a workshop back 30 years ago in Kingsville.
Back when Kingsville was A and I?
Yeah, it was still A and I. Yeah.
Okay. Huh.
Right, with rational exponents. Okay.
Number 11. Okay, so you got to keep looking over here to see the problem number. Maybe y'all aren't interested in the problem number, but I like to have it labeled when we're working it out. We're doing problem 11.
The square root of 23. They want us to write this, switch over,
with rational exponent.
Okay, that's 23. What's the exponent I'm going to put on the 23? A half. Okay, a square root is the same. A square root is the same thing as the exponent of 1/2. So
when we're working with logarithms, we're going to be going backwards like that a lot. You've got to know if it's a square root, that's a 1/2 exponent. If it's a cube root, a 1/3, and so forth. I'll be quiet.
But that's Tony's right. That's going to be your little bag. You're going to add that to your bag of tricks. When working with logarithms, every time you see a radical, you're going to have to write it using an exponent. So you'll be going backwards when working with logarithms. You'll have radicals. The first thing you'll have to do is write it using an exponent. So did you type in that answer?
Not yet. So all I'm going to type in is 23.
Shift up. You can just do a shift up if you don't want. Oh, well, okay.
I like it doing it like that.
Okay, well, I do the shift up there. It's quicker for me, at least.
Like this and this.
Mm-hmm.
Oh, okay.
And just like a superscript that's a shift down arrow. Okay. Oh, rewrite using a rational exponent. We're just barely 30 minutes into it, and we're already on problem number 12. So, wow. Yeah. These problems are pretty short. Okay.
This assignment in particular has both the foundations problems and the college algebra problems all mixed together.
Okay. Yes.
You're taking 2 classes.
They're taking 2 classes. This is a blended class, and so some of the problems in this assignment are college credit, some are the foundations. They want us to write that using a rational exponent. What exponent am I going to put on this 18? I'm not going to say anything. Y'all are going to tell me. 1/4. A 4th root is the same thing as a 1/4. A 4th root is the same thing as an exponent of 1/4. Oh, I keep forgetting to box my answers in.
18 to the 1/4 power.
And I need to write some now. The name of this assignment, is it Exponential Functions? Is that the name of the assignment? Well, we better define what we mean by an exponential function.
Better have something to do with an exponent.
Surely it does. Let's see. An exponential function.
By the way, he's now moving into the college algebra.
I wasn't going to tell him that. It's blended. Okay. Loosely speaking, an exponential function is any function that has a variable in the exponent position. It has a variable in the exponent. I'll just say in the exponent. In order for a function to be exponential, it has to have a variable in the exponent. We've seen things like this. F of x equals x squared. We've seen the variable in the base, and the power is just a number. That's what, quadratic? We've seen something like this. F of x equals 2x. Now, what would that be? It's just 2x. If I were to graph that, what would I expect to get? Y equals 2x. First things we graphed. Maybe a line. That's a linear function. An exponential function would be something like this one here. F of x, instead of x squared, something like 2 to the x. This thing is exponential because it has the variable in the exponent. We're going to first thing we're going to do with exponential functions, we're going to graph exponential functions, and then in the rest of the assignment we're going to be solving exponential equations. But first of all, let's graph exponential functions. We're graphing exponential functions. Let's go to number 13. Oh, we don't have an exponential graphing tool in this course, so it's going to be the multiple choice problems. What we're going to do to graph exponential functions, we're just going to plot points and just connect those dots, okay? Once we see a path. Y equals 4 to the x. That's the thing we're trying to graph. We want to graph y equals 4 to the x. Let me write this down. And I'm just going to plug numbers in for x and plot points until I see the shape of the graph. I'm going to make myself a table of values, x, y, and I could plug in any number I wanted to for x. I could plug in 10, 4 to the 10th power. That's getting sort of big. I'll go ahead and write down 3. Generally, the integers from 3 to negative 3 are enough to give you an idea of what the graph looks like. In this case, we may not want to plot all of these points. You'll see what I mean as we start determining the y values. You take the 3, you plug it in for x. So you're going to have 4 cubed. Plugging in the 3, we have 4 cubed. 4 times 4 times 4, is that 64? So we have a y value of 64. The first order pair I found was right 3 up 64. Oh, I don't think I'm going to bother plotting that point, okay? What's the second y value that I'm going to get here? Plug in the 2 for x. That's going to give us a 4 to the 2, which is 16. Oh, goodness. I don't think I'm going to plot that point either. I don't want to count up 16 units. I like this one. Plug in 1 for x. What are you going to get? 4 to the first power is 4. Oh, I like this one too. Plug in the 0 for x. Be careful. Remember the first thing that we said today in class. What was the first thing we did? We said 4 to the 0 power is defined to equal 1. That's correct. Now we're getting into the negative exponents. So we've got to remember our properties for negative exponents. You plug in the negative 1. 4 to the negative 1. 4 to the negative 1. How do I write that without a negative exponent? Where is it? 4 to the negative 1. That's the same thing as 1 over 4 to the positive 1. You drop that negative, you get rid of the negative on the exponent, but you pick up a 1 over. So that's a 1 over 4 to the first power, which is just 1/4. So when we're drawing our graph, we're going to have to go left 1 unit and only up 1/4 of a unit.
Ooh.
And is this too small? Can y'all see that? Do you need to blow that up a moment? Can y'all see that better now? Now let's plug in -2. I'll let y'all tell me what that equals. 4 to the -2 power. That's 1 over. Let's get rid of the negative, but pick up a 1 over. What have we got down here? 4, I think I heard it, to the 2, so 1/16. So we're going to go left 2 on the x-axis and up only 1/16 of a unit.
I think you've done enough.
Well, what about 3? Oh no, pardon me, that's -3. Plugging in -3, that's 4 to the -3 power. That's 1 over 4 to the positive 3. And we already said 4 cubed is 64. So 1 over 64.
Oh, wow. How are you going to go up 1 over 64 units?
Notice, the more and more negative we get, the smaller the y value is getting. We go left 1, we go up 1/4 of a unit. Then we go left 2, only up 1/16 of a unit. Left 3, we're going to have to go up 1/64 of a unit. That's so small, it's probably going to look like the point sitting on the x-axis. Let's draw our xy grid. Oh, before we go on, a positive number to any power. If you have a positive number to any power, doesn't matter what the exponent is, what sort of a result do you expect to get? Are you ever going to get any negative y values? That's the question. I guess that's the question I'm trying to ask you. Will these y values ever become negative? A positive number to any power is always a positive number. So we're not going to get any negative y values here. The y values, they're going to keep getting smaller and smaller, but they're never going to become negative. What about 0? Is there a number you can plug in to make this thing equal 0? 4 to any power, a positive number to any power, it's not going to equal 0. It has to be positive, greater than 0. And that'll be significant in a moment. Let's draw our xy grid. And since we don't have any negative y values, I'm going to just draw the grid showing there. I think that's good enough. Remember, we just got to get enough of the graph drawn to be able to pick out the correct picture. So it's multiple choice. As I said, oh, here's 1, 2, 3. I'm not going to bother trying to label right 3 up 64. We go right 3 up 64. That's way off the top of this page here, okay? So I'm not even going to bother plotting that point. 216, that'd be right 2, somewhere right up here, I guess. I'm not going to count it. That's 16 units. I'm not going to use either of those. I'm going to start right here.
There it is.
Right 1. Oh, you found 216?
Right 2 up 16. Right
okay.
there.
Okay.
We're not going to plot it.
right 1, up 4. Okay. Then left, right, 0, up 1. There's my y-intercept. Now the interesting part of the graph is this left side here. We're going to go left 1 and up a 4th. So we go left 1. Imagine breaking this little interval here into 4 equal subintervals. That's how you would go up 1/4 of a unit. Okay, I'm just going to sort of eyeball it. It would be right out there. Then we go left 2. I labeled that one. I labeled that one. This one. We go left 2 up 1/16 of a unit. I think to the naked eye, it probably look like this one is sitting on the x-axis also. You go left 2, break that interval into 16 little subintervals. So it'd be right there at the x-axis, wouldn't it? Just barely up. And at -3, you go up even less. Imagine breaking that one interval into 64 equal subintervals. You're just barely off of that x-axis. Now, it can't pass through because we said there can't be a negative y value. A positive number to any power is always going to be positive. And it's not going to equal 0. Now, these y coordinates are extremely close to 0, but they're not exactly equal to 0. So, there's the graph. Now on the left side, this side here, the graph continues going on and on forever, and to the naked eye it's going to look like it's sitting on top of the x-axis. But technically there's always a tiny bit of space, because a positive number to any power will always be positive, not equal to 0. It's not going to be a flat 0. We say that the x-axis is an horizontal asymptote, asymptote. We also say the graph approaches the x-axis asymptotically. What you're going to want to remember, something that you can remember that will make these graphs a lot quicker. You should expect one side of the graph to be growing very fast. It should be very steep, almost vertical. You should expect the other side to be very flat, almost horizontal. If you remember that generalization, then you can get these graphs drawn very quickly. One side's going to be real steep, up and up. Think about it. At 3, we're way up at 64 up here, so it's very steep on the right side, and in this case, the left side is the flat side. Any questions on my logic here? Let's choose the correct response. I think there's only one that comes even remotely close. A, B, C, or D? C? They can see that it's C.
It's not B. Is it C? It's sure not D. Do you see D? It is C. And look, you see it looks like it's sitting on the x-axis, doesn't it?
But technically there is a space between that blue curve and the x-axis.
See?
If you remember the generalizations I said, one side you expect to be very steep, almost vertical. The other side, very flat, almost horizontal. You can get by with maybe 3 points. My advice, I'm going to use 1, 0, and -1. Those are the numbers I'm going to be using to generate my ordered pairs. And when you look here, okay, when you look at this, the way it's rising from left to right, when you're rising from left to right, you hear about exponential growth. Population grows exponentially. That means it's real slow at first. For thousands and thousands of years, there were very few people on this planet. But eventually, it starts growing. And we're now at that steep part right now in terms of population growth. During our lifetime, it's gone from 4 billion to 5 billion to 6 billion to 7 billion. Are we 8 billion yet? Yes, we are. You see, it took millennia to get up to 4 billion. And now we've grown 4 billion during my 60 years and my 60-year life. That's what they mean by exponential growth. It starts real slow, then starts going real fast, eventually. Number 14 is we're going to graph y equals 6 to the negative x. One side you expect to be very steep, the other side you expect to be very flat. If you remember that, all you have to plug in to get a good shape, idea of the path, you can plug in 1, 0, negative 1. I think 3 points is sufficient.
If you use
If
anything
you know,
bigger, like 2 or 3, you're going to be getting such big numbers.
plugging in 1, we have 6. Don't forget about that negative sign there. 6 to the negative, we're plugging in the 1. 6 to the negative 1. What does 6 to the negative 1 equal? Write that without a negative exponent. That would be 6 to the negative 1 is the same thing as to get rid of that negative, to change it so that the exponent, you don't have a negative exponent, you have a 1 over, and then what do you have in the bottom? The negative became the 1 over, and then in the bottom you have 6 to the first. And 6 to the first is just 6. So 6 to the negative 1 is the same thing as 1/6. What are you going to get when you plug in that 0? Okay, 6 to the, that would be a negative 0. That's just 6 to the 0, which is 1. And now be careful. You have a negative 1. You're plugging it in up here with that negative. That's a 6 to the negative 1. What's that going to give us? A positive 1. 6 to the first power is just 6. Any questions there? And I claim we can get a good picture drawn just with these 3 ordered pairs. Once again, we have no negative y values, so I'm not going to draw, I'm going to just focus on the top half of the graph. This says, go right, move up 1/6, right 1 unit, up 1/6. It's just barely off the x-axis. 0, 1, where is that point located? Right there on the y-axis at 1. And then left 1, up 6. Left 1, up 6. 1, 2, 3, 4, 5, 6. Can y'all tell which side is going to be the flat side and which side is going to be the real steep side? Yeah, I think we can tell now. Oh, look at that. I did that. Blow that up. Look, so they can see. I tried to show that technically there's always a space between the curve and the x-axis. In this case, the left side is the steep side, the one that's pulling away from the x-axis. The right side is the flat side, the one that looks almost horizontal. Any questions there?
Look at all these answer choices.
I bet
it couldn't be B. That doesn't have one, it doesn't have that right shape, correct shape. Which one does it look like?
C again?
Is it this one? Is that it? See, I notice it's only showing between 5 and negative 5, so it doesn't even have 6 drawn up there. This one's it.
Response C. Any questions? Now, I need to talk some more and write some more. Oh, so to summarize graphing, just plot enough points to see the path, okay? And if you remember the generalizations I mentioned, you should be able to get by just 3 points. Use x equals 1, x equals 0, x equals -1. That should give you a very good picture.
It's one side's vertical, one side's flat.
Exponential equations. An exponential function is a function with a variable in the exponent. An exponential equation is an equation with at least one variable in the exponent. Equation with variable in exponent. And there are two generally accepted methods of solving exponential equations. The first method is the same base method. That's what we're going to see today. On Monday, 1 week from today, we'll see the second method that requires logarithms, but we haven't started logarithms yet, so we're not using logarithms to solve these equations. What we have is the same base method. A very logical method if you think about it. Here's what the same base method says. It says if b to the x is equal to b to the n, then if the bases are equal, the only way the left side can equal the right side is for the powers to be equal. That x has to equal n. And I told them, Tony, that you needed to be quiet. The more you talk, you start those coughing spells. And they said I should use packing tape and just tape your lips shut then. Wow. Don't be mad at me. That's what they said. Okay? And if you think about this, it makes sense. It's a very logical method. Look at this. Suppose I wrote, here's the question. I want y'all to solve it for me. 5 to the x is equal to 5 squared. What's the only number you could put in there for x so that the left side of this equation equals the right side? It has to be a square. If the bases are equal, the only way the left side can equal the right side is for the exponents to be equal. So x would have to equal 2. The problem is they're not going to give you problems like that. You're going to have to use your properties of exponents that you've seen today so that you can get the same base on both sides. For example, number 16. We'll go back to 15 in a moment.
Oh, okay, 16. Okay. Wait. How do I skip? Oh, gosh, I don't know. There. Oh, this is a good one.
I know.
Solve this equation analytically.
This is number 16. Let me write it down. 2 to the 2x minus 1 is equal to 16.
Goal is to get x equals a number.
That's right. Well, your first goal, though, is to get the same base on both sides. In order to get to solve an exponential equation using the same base method, you need the same base on both sides. Now, the base is the number that's written down low. The exponent is the thing that's written up high. So we have two different bases. You have a 2 and you have a 16. You say, well, there's no power on that 16, so how is it a base? Sure, it's a base. There's that assumed power of 1. My advice to you, Okay, look at the smaller base, 2. 2 is a prime number. You're not going to write 2 as a power of anything other than 2. You better be able to write 16 as 2 to a power. 2 is a prime number. You're not going to change that. You better be able to write this as 2 to a power. Can we do that? How do we write 16 as 2 to a power? Don't say 2 to the 8th power. 2 to what power gives us 16? If you're uncertain, dig your calculator out. And I'll tell you right now, you have to be able to get a common base here. So you've got to be able, and 2 can't be changed, so you better be able to write 16 as 2 to a power. How do we write 2 to a power?
How many 2's do we
Maybe 2 to the 4th, 2 to the 4th power. 2 to the power 4 is the same thing as 16. And now you have the same base on both sides. The only way they can be equal, if the bases are equal, the powers have to be equal. That means 2x minus 1 has to equal 4.
So you're dropping the big 2's.
You drop the big 2's. You're dropping the base. Once you have the same base on both sides, you drop the bases. You set the powers equal. And this is just a little linear equation that's simple enough to solve. The work for these will be getting the common base. Once you get the common base, the rest of it is algebra that should fall out pretty quickly. I'd add 1 to give me 2x equals.
How will we solve this equation?
2x equals 5, I agree. And then what will I do? Divide by 2 to get the x by itself to give us x equals 5 over 2 for our answer. They didn't really tell me to put packing tape over your mouth.
I'm mad at him anyway. I'm grouchy, but it's the steroid shots, okay? Oh, wait, no,
okay,
no,
we need to go back to 15, but I need to write something first. I need to... Oh, gosh. There's something called the power rule of exponents, and this is going to be important. There's a power rule of logarithms that's a direct result of this power rule of exponents. So you need to remember the power rule of exponents. If you have a power, say a base, raised to a power, raised to another power. If you have a power raised to a power, if you have a power raised to a power, to simplify, so that you don't have parentheses, to write it as a single power, you keep the same base, and you multiply the powers, a times n. A power raised to a power, you multiply. And that's going to be important.
How about x squared cubed?
Yeah, let's see. For example, x squared all cubed. Well, using this property, power raised to power, you multiply. That means we have how many factors of x? X to the 6th, 2 times 3, so that's x to the 6th. Now, let's see, why is that the case? This is saying you have 3 factors of x squared. We have time on justify. That's saying we have 3 factors of x squared. And we know that 3 factors of x squared, that means 1, 2, 3. We have 3 factors of x squared. What does x squared mean? What do we mean? X times x. So x squared is x times x times another x squared, x times x times 2 more x's. How many total x's is that? 6, so x to the 6th. A power raised to a power, you multiply to get a single power.
So this rule is just a shortcut so you don't have to do this and count every time.
Right. And you can apply it when you have negative exponents. You don't have to try to convert it to a positive exponent.
Or have fractional exponents too.
That's right. It's a good point. Go back to number 15, please. Did you like the way I said please, Tony? I decided I'd try to be more polite to you. 9 to the x equals 3. Okay, it's an exponential equation, and the variable's in the exponent. We need the same base on both sides. 3. 3 is a prime number. You're not going to change 3. Well, what's the exponent up here on this 3? I don't even see an exponent on that 3. What do we assume it is? 1, yeah. But we need this number written as 3 to a power. How can we write 9 as a power of 3? 9 is the same thing as, how do you write 9 as 3 to a power?
It's not a hard question. 3
to the power of 2, and it's all 3 squared. There. Did y'all follow my logic here? 9 is 3 squared. 3 times 3 is 9. Why did I mention this power rule of exponents? What have we got here now? 9 was replaced with 3 squared, but we still have that exponent of x. A power raised to a power, what do you have to do?
Starts with the n.
Power raised to a power, we not add it, multiply. You multiply, when you have a power raised to a power, you multiply the inner power by the outer power. A times n gives you an an. 2 times x has given us a power of 2x. I think y'all are having trouble with this number 15, and it's not really supposed to be a difficult problem. 9 is 3 squared, and now we have a power raised to a power, so we multiply. What can we do at this point now?
Are we going to write any more 3's? Say no. No. Okay.
You have the same base on both sides. If you have the same base, you drop the bases, set the exponents equal. So 2x has to equal 1. Divide both sides by 2 to give us a final answer of x equals 1/2. Any questions there?
See how we rewrote the 9.
That's the job. That's the work here. The real work is trying to get a common base on both sides. Because once you get to this point, common base on both sides with no parentheses, dropping the base, solving the equation's pretty straightforward. It's getting to this point right here. You have to use your properties of exponents to get a common base on both sides.
Because you're trying to get that statement right there.
Same base on both sides, so you can drop it and set the exponents equal. And I'll tell you right now, that's the only method we have for solving exponential equations at this point. You have to be able to get a common base.
But if you're wondering, what if there'd been a 7 instead of a 9?
Well, let's just look at this one right here. I'm going to make up a real straightforward one, I think. 2 to the x is equal to 7. What can we use? Can we use the common base method here? 2, that's the smaller base. I always start with the smaller base and try to get to the bigger base. 2 is prime. You're not going to change 2. Can you write 7 as 2 to a power? You're asking yourself, 2 to what power will give you 7? 2 squared is 4. 2 cubed is 8. 2 squared is 4. 2 cubed is 8. Well, 7 is between 4 and 8. So the exponent has to be between 2 and 3, but it's a irrational number, so we don't know what that is. Here, you cannot get a common base. I'll say the same base method fails.
So all of these are rigged so you can get that common base.
Something like this, 1 week from today, you'll see how we solve it using logarithms.
And you'll think, oh wow, that ain't hard at all.
Let's go on to number 17.
Let's see, we've done this one. Gosh, I hate this. There's not the little arrow to move on. Okay, there. Okay. Oh, this is a
3 to the 2x minus 5 is equal to 81. 3 to the 2x minus 5 is equal to 81. What do y'all think we'll use as a common base? The two bases we have, on the left side we have a 3. What's our base on the right side? And 81, well, we bet 3 is a prime number. You're not going to change 3. You better be able to get a 3 over here. Can you write 81 as a power of 3? You're asking yourself, 3 to what power will give you 81? Any ideas? 3 to the 4th power. Good. 81 is the same thing as 3 to the 4th. And on the right we have a 3 to the 2x minus 5. What can we do now? Drop the base, set the exponents equal. We have a common base on both sides, no parentheses. If we had parentheses, we know what we have to do. If we have parentheses like that power to a power, we got to multiply. But there's no parentheses here. We just drop the base, set the 2x minus 5 equal to 4. We can add 5 to give us 2x equals. So adding 5 to get 2x equals 9. Okay, 4 plus 5 is 9. And then what do we need to do? Divide by 2 to get our final answer of x equals 9 over 2. Any questions there?
Common base.
This is the common base method, and the problems have to be set up in a way so that you can get a common base. No, number 20. Number 20. Oh. Hey, this is the first time we've seen an equation where there's a variable on both sides. We have 81 to the 3x minus 3 equals 729 to the, is that an x plus 3? Oh. Well, we have, what are our two bases? What numbers are acting like the base? On the left we have 81, and on the right we have 729. Well, let's see, 81's the smaller one. 81 to the first power is 81. Do you think 81 squared will give us 729? Punch that into that calculator of yours. No, it gives us something real big. This means we're going to have to change the base on both sides. Sometimes you have to change both of them. Stop and look at 81. 81, how can you write that using an exponent? One thing comes to mind when I see 81.
Right from the multiplication tables.
Yep, right from the multiplication tables. Maybe what times what equals 81? 9 times 9. Well, 9, can you write 729 as 9 to the power?
So 81 is 9 squared.
Okay.
Let's start multiplying 9s and seeing.
9 squared is 81. Can we write 9 to the power equals 729? What do y'all think? Hey, look at that. So what is that? 9. I would have used 9 cubed. That's 9 cubed. That's not too bad. So we can use the new common base of 9. 81 is the same thing as 9 squared all to the 3x minus 3. Y'all help me out here now. 729. What am I going to write in here? 9 cubed. 9 cubed. And I still have that x plus 3 on the outside. There. 81 I wrote as 9 squared. 729 I wrote as 9 cubed.
This is another one of those times when you're just making this stuff work out.
Yeah, you're right. I'd keep on. And this is an interesting problem because you could use a base of 3 also.
But that's going to give you big
That's going to give you bigger numbers, and I would recommend it. But you could have used a 3, and you would have still got the same answer at the end. You'd have a 3 to the 4th here, and a 3 to the 6th. 3 to the 6th. I like using 9 better. That keeps the exponent smaller. Okay, there's only one correct next step. We have powers raised to powers. What are we going to have to do when you have powers raised to powers?
How do you get rid of the parentheses? I heard multiply.
Okay, so you're going to multiply 2 times 3x minus 3. Well, tell me what you're going to do. How are you going to multiply those? It starts with a D. Distribute. Okay. Take the 2 times the 3x minus 3. What are you going to get when you multiply 2 and distribute it over 3x minus 3? 6x minus 6. Good. Apply the same logic on the right-hand side. What are we going to get? 3x plus, I couldn't hear you. 3x plus 9. I agree. Any questions on our logic? Because all of this stuff here is the new stuff we've done today, okay? Because what are we about to do? We have the same base on both sides, no parentheses. What can we do? Drop the base, set those exponents equal. At this point, it's just the same stuff that we've run into before. We have a linear equation that we need to solve. I think I'll move this 3x over to the left by subtracting 3x. What's that going to give me? Do it in your head. You have a 6x minus 3x. What are we left with on the left-hand side? 3x. What am I going to do with this minus 6 here to get it over here? 9 plus 6 gives me 15. Any questions on our logic there? We combined the x terms together on the left. The thing that didn't have x's, the constant terms, we put on the right. And now, divide by 3 to give us x equals 15 divided by 3 is 5 for my final answer. Any questions there?
Wow, that was a really important one. 5
Okay, any questions? I need to write some more. There's so much good algebra in this.
I think you must have hit that.
Oh, I did hit it. Uh-oh. Hasn't been like that, I hope, has it?
I don't think so. I would have noticed.
Okay. An irrational number is a non-repeating, non-terminating decimal. I remember hearing that in elementary school, and I remember thinking, no, I guess it was in middle school, and I remember thinking that's nonsense. And non-repeating, non-terminating, there are only 10 digits. If the digits are going to keep going forever, they got to repeat. But they mean no repeating pattern. An irrational number. How are we doing on time?
It's 3:33.
Oh, we're doing real good. It's a non-repeating, non-terminating decimal number. Non-repeating, non-terminating decimal number. And I guess the most famous example of an irrational number is pi, the ratio of the circumference of a circle to its diameter. That's where we have to use that little symbol, 3.14, blah, blah, blah. It just keeps going. The digits keep appearing forever. And we've been working with irrational numbers since the beginning of the semester. Even though we haven't run into pi this semester before today, any square root that's not a perfect square is an irrational number. The square root of 2, that's irrational. Square root of 3 is irrational. What about the square root of 4? Is that irrational? No, the square root of 4 is what? 2, but the square root of 5, and so on. There's another irrational number, one that you've probably not run into before now. It's called the natural exponential. Exact values of irrational numbers have to be represented using a symbol because you can never write out all those digits. The symbol they decided to use to represent the natural exponential is the lowercase letter e, and its approximation is 2.718.
This is a decimal approximation for it there. 2.718281828. It looks like it's about to repeat.
And then it begins to
4590452. And the reason they used the E is because the mathematician that used it, Euler, first, his last name began with an E, so he said, like if I were the one discovering that number, I would have called it a P for Precella, but I didn't discover that.
Mm-hmm. Okay.
For our purposes, you don't have to remember the approximation. You need to know that that letter E is not a variable. It's representing a number. E is irrational. You're not going to write E as a power of anything other than E. So if you have a base of E, you better have a base of E on both sides if you're going to use the same base method. And to illustrate, I've lost my list where I wrote out the order I wanted to do. So go back to the 18, I guess. There.
Number 18. This is not as bad as it looks.
Actually, pretty
because
darn
you know what the common base is going to be. E to the 6x minus 1 is equal to e to the 4th power all raised to the x. Make sure I didn't miscopy that. Yes. Okay.
So, if there's an E in it, E better be the common base.
And we have the E on both sides. The only problem is we can't just drop the E here because we have a power raised to a power. We know what to do when we have a power raised to a power. What are we going to do? You multiply, that's right. 4 times x is 4x. Now we have the same base on both sides. The same base on both sides with no parentheses. You drop the base, set the powers equal. So 6x minus 1 must equal 4x. Oh, I think I feel like moving that 4x over to the left.
Don't have all those
Negatives, yeah, that's what I'm thinking. That'll be a 6x minus 4x. What do I have here on the left? 2x, okay. What am I going to have on the right? What are you going to have to do with that minus 1? Add 1, so you have 2x equals 1.
Look at the little red arrows. You know how I love my arrows. That's my contribution to today.
And then what? Only one thing left to do. We moved the 4x over. 6x minus 4x gave us 2x. We moved that negative 1 over. It became a positive 1. And now we divide by 2 to give us x equals 1/2. For my final answer. If you have an equation with an e in it and you're trying to use the same base method, you better have an e on both sides. Number, is it 19? Oh, here's my number 19. Oh, well. How are we doing there? Is it similar? Is this one pretty similar to the one we just did? What do y'all think? Yeah. E to the 13x minus 1 equals e to the 11 raised to the x. So what am I going to do first? Okay, 11, this one here, that e to the 11th to the x, I'll write that as e to the 11x. And then what am I going to do? Drop the bases, set the exponents equal. So we have 13x minus 1 is equal to 11x. We'll move the 11x over. We'll move the minus 1 over to give me 13x minus 11x is... Oh, this is looking familiar, isn't it? What am I going to have on the left side? 2x. What am I going to have on the right? 1.
Well, that just...
And that gives us a final answer of 1/2.
Well,
once again,
don't decide, if there's an E, the answer is 1/2. That's just a coincidence here. Let me see. 1/2. Oh, wow. Well, we're going. 20 short years. We'll be through.
Let's see. We're
down to the last 3.
Number 21.
Ooh, it looks really bad, but what makes it look worse than the other one?
Instead of that fraction,
that 1 over. Did we learn something we can do to write it without a 1 over?
Okay, wait a minute. Let me make sure I've written 1 over e to the negative x equals 1 over e cubed. Okay.
Do this one first. I think this one.
Okay, I'll do that one first. Notice we have e's on both sides. I'll tell you right now, when using the same base method, I do not like a base that's a fraction. I don't like the 1 over e and the 1 over e cubed. We have a way of rewriting this 1 over e cubed just as e to the power. Let's do the right-hand side first.
Does anyone remember? What do we do to get rid of that 1 over?
We do something to the exponent. We drop the 1 over, and we do something to that 3. What do we have to do? Make it negative 3. There's so much to remember here. At this point, I'm afraid this stuff is just hitting y'all in the face and bouncing off. So, at the end of class, someone will ask me, did you get it done, the assignment? I'll be like, yeah, I got it done. Didn't do it well, but I got it done. Let's see, we're going, oh, okay, 1 over 7 squared. Remember the way we said that's 7 to the negative 2? That's what we were trying to prepare y'all for. This notation, 1 over b to the n. You drop the 1 over, and you make it a b to the negative n. That's what we just did here. Any questions? We need to write this thing here as e to the power also. We have an e.
Hey, but there's not an exponent on it.
Hey, I don't see an exponent on this e right here. What's the little assumed power we have? If you don't see an exponent, you assume it is a 1.
Now that he's written the 1, is it just like this one?
What do I put here? A negative 1.
Good.
Okay.
Any questions on there? This is all building slowly. And so,
any questions? Because at this point,
it's like the other one. Get rid of the parentheses.
Okay, we have the base of e on both sides. Any questions before we go on? The key to the problem is the way we rewrote the 1 over e is e to the negative 1. The 1 over e cubed is e to the negative 3. Any questions on how we did that? Okay, there's my e's. Y'all tell me, what are we going to do? We have powers raised to powers. Powers raised to powers. What do we do when we have a power raised to a power? Multiply negative 1 times negative x gives me a positive 1x. Here we're multiplying negative 3 times x plus 7. What are we going to have to do there to multiply? Distribute the negative 3, so that's negative 3 times x, which gives me a negative 3x. And what else? We have a negative 3 times a positive 7. What's that going to give me? Okay. Is that plus 21? I think it's a minus 21. Negative times positive gives me a negative 21. All the times you've been right, and I didn't say, good, Jonah, good. But the one time you say something wrong, you pounce. Those are good teaching tips, okay?
So that's really a bad tip.
That's a bad teaching tip. I know. Oh, goodness. I've been dreading this class today because I knew it was a long one. I knew there was a lot to say. So y'all tell me, what do I do now? Drop the e's, set the x's equal. And I'll move that minus 3x over by adding 3x. What am I going to have here then? 1x plus 3x gives me a 4x equals a negative 21, and then divide by 4 to get the final answer of negative 21 fourths. Negative 21 fourths. Any questions there? Y'all are so quiet.
It's a lot.
Yeah, it's a lot to think about. Any questions there? Any questions?
Key was to get it written E equals E.
And to do that, to get rid of that 1 over E and 1 over E cubed, you have to write it using negative exponents. But once you do that, it works out pretty nicely. Any questions there?
Get rid of a 1 over, make the exponent negative.
Negative, that's right. Just drop the 1 over and make the exponent negative. Okay, number 22.
They're thinking, oh gosh,
Can it get any worse?
can it get any worse?
Oh, they're not thinking that.
And it can get worse. There's a square root in this one now. But we're not going to panic.
Because I told y'all that there's a trick that we're going to use with logarithms. Every time we run into a square root with logarithms, we're going to pull this trick. And we were working with radicals earlier today. Remember what I said. When you see a square root, you need to start thinking of that as a rational exponent. That square root of 3. Where is it? We wrote out our rational exponent. Oh, wow. There it is. We can write the square root of 3 as 3 to the 1/2 power. Remember I said a square root is the same thing as an exponent of 1/2. Right here. We had the square root of 23. How do we write that? We wrote it as 23 to the 1/2 power. And I told y'all, add that to your bag of tricks because that's what you're going to be doing with logarithms. Whenever you have a radical in a logarithm, you're going to want to write it using an exponent. If it's a 4th root, it's an exponent of 1/4 and so forth. But for our purposes, this is a square root of 3. I'm going to write it as a 3 to the 1/2 power to the x plus 6.
So what you're telling me is the base is a 3 on the left.
The base is a 3 on the left and a 27 on the right. Well, what are you going to use as your common base? 3 is a prime number. Can you change 3? No. So what about 27? You better be able to write that as 3 to a power. You're asking yourself, 3 to what power will give you 27? 3 to what power? 3 squared, we know that's 9. What about 3 cubed? What does 3 cubed give you? There it is. 3 cubed is 27. So we have a 3 cubed, and what's that exponent there? An x. I wrote the square root of 3 as 3 to the 1/2. I wrote 27 as 3 cubed. Now we have a power raised to a power. On both sides, what are we going to have to do? We can't drop the 3's yet because we still have parentheses. Powers raised to powers, we will multiply. So I heard someone say we're going to distribute the 1/2. 1/2 times x is 1/2 x. Plus, what's 1/2 times 6? 1/2 times 6 is 3. 1/2 times 6. The 2 goes into 6 3 times. So that worked out nicely at least. What have we got on the right-hand side? We have a 3. Power raised to a power, what's the exponent? 3 times x is 3x. Any questions here? No? You have the same base on both sides without parentheses, so we drop the bases, set the exponents equal. 1/2 x plus 3 is equal to 3x.
And you're thinking, oh no, there's a fraction here.
what should we multiply through by in order to cancel out that fraction? Let's do that. Let's get rid of the fraction right now. What would we multiply through by? To cancel out that 2, it should sort of be obvious. What can we multiply through by? This is an equation. We can multiply both sides by this number and it'll cancel out that fraction. What will we multiply by? What's the least common denominator?
What's
the only denominator is a 2, so that means we're going to multiply by that denominator 2. How many times are we going to have to multiply by 2? How many terms do we have? On the left we have 2, on the right 1, so we're going to have to multiply 3 times. So times 2 over 1, times 2, and times 2. And trust me, after all the years of experience, I find students doing this, multiplying and getting rid of the fraction now, they have a better chance of getting the correct answer. Cancel the 2, so you just have a 1x plus here.
6.
3 times 2 is 6 equals here 6x. I think I'm going to move the x to the right. I'm going to try to decrease the number of negatives. So, moving the x to the right, we're going to have 6 equals, what are we going to have to do to move that x to the right? It'll be 6x minus 1x. What are we getting here? 5x. There's only one thing left to do. Divide by 5 to give us x equals 6 over 5. Any questions there? Switch back, let them look at this work once again. Any questions there?
Looks like 23 is really, really similar.
Oh, let me see. Let's see number 23.
Hey, you know what? Let me see if I can change it and
make it a little different.
Okay, close that. Oh, it didn't. It used to be you click here.
Yeah, that was a good one, but now it's too late.
Oh, I like that one.
Okay.
Okay.
Number 23.
And this is the last one, so it's got to be the hardest one. But actually, it's very similar to the one you just did. The last two problems, I guess you can look at this number here and figure out. We assigned the same problem with them, given different numbers.
Okay. Switch to my paper. This is very similar to that last one. What am I going to do first? What do y'all think I'm going to get rid of the square root? That square root of 3 is the same thing as 3 to what power? The 1/2 power.
Good.
And we still have that x plus 2 there. 81, we need to write that as a power of 3. Three to what power gives you 81? 3 to the 4th power.
See, 3 to the 4th is the same thing as 9 times 9, isn't it? That's why 3 to the 4th is 81.
And then what will we do?
Yeah.
Okay, so wait. 3. Here we go. We're distributing the 1/2 times the x plus 2. 1/2 times x is 1/2 x plus 1/2 times 2 gives me 1/2 times 2 gives me 1. Here, what are we going to have as our exponent? 4x. Now what can we do? What can we do? Drop the bases, set the exponents equal. So we have 1/2 x plus 1 is equal to 4x. You could work with the exponents if you wanted to, but my advice...
4x minus 1/2 x.
Yeah.
What would get rid of the fraction? Multiply through by
2. So, and how many terms do we have? How many times do we have to multiply by 2? 3. So we multiply by 2, multiply by 2, and multiply by 2. The 2's cancel to give me a 1x plus, here, 1 times 2 is 2, equals, here, 2 times 4x gives me 8x. What do y'all think I'll do next? Move the x to the other side. 8x minus 1x is going to give me a 7x equals 2. Only one step left. Divide by 7 to give us x equals 2 over 7 for my final answer.
2 over 7. And we're finished and it's not yet 4 o'clock. Oh, wow, okay. So
Any questions there?
It's a lot. It starts off pretty, and even then, it's not that hard or bad. What this?
It's not that long. It's sure not a cut point method problem or completing the square to find the center radius of a circle problem.
If you work through the assignment like this, it builds you up to this stuff. Don't jump to number 23 as your first problem to do. Work through it, and it just sort of builds you up to it. And the stuff we thought was going to be really hard, you have 2 of the exact same, like 22 or 23. So just to give you a little extra practice. Are there any questions for Tim to answer?
Okay. Well,
okay, then I'm going to stop recording it. And if you have any questions,